Welcome to lecture 1 of module 5. In this module, we are going to discuss on natural / free convection. Heat transfer. Now, in this module, what we are going to discuss in this first lecture is to discuss about that basic concepts of natural or free convection heat transfer, the theoretical concepts. Natural or free convection heat transfer. Now, as we understand, convection heat transfer we have discussed previously, and where that which is also called as forced convection heat transfer. In our module 4, we have discussed this. In case of forced convection heat transfer, a fluid is having a velocity, it moves with a velocity, therefore, the particles of the fluid moves with the help of a velocity. So, then external applied force is there in that, therefore, the fluid has got a movement, and therefore, it is called a forced convection heat transfer. But in this present situation, it is called as natural or free convection heat transfer. It means that the fluids are moving, fluid elements are moving due to some natural process. Now, what is this natural process in this particular case, or free process in this particular case, is that we are not putting any external force for the movement of the fluid, but what happens in this case is that due to the fluid moves due to the movement due to the differences in the densities. Okay. As the fluid particle gets heated at the bottom of a surface, if the fluid particle gets heated, then it will become lighter in density, and as it becomes lighter in density, it will try to move upward, and heavier particle which is of at lower temperature, which is in the upper region, that will try to come back and take the position of the hot particles which is going upward. So, this is the kind of circulation that may take place. Okay, that is the phenomena. This is happening in case of natural or free convection heat transfer. So, it is a natural process, because many a times we have seen that particularly in case of earth environment, we know that earth surface gets heated up, and then there will be a convection that can take place. So, that heating of the surface, if it is a very natural phenomena, then automatically the particles will move upward, and there will be circulation, there will be flow of the fluid particles. That is why it is called natural convection. Sometimes it is also called free convection, because there is no external force being applied for the movement of the fluid. At the same time, when this free convection or natural convection takes place, now when the fluid particle moves from one place to the other place, then it is carrying the it is carrying the thermal energy along with it, and therefore, this thermal energy is being transported from the one place to the other place. Like this way, therefore, you can have a heat transfer also, and therefore, this kind of heat transfer is called natural or free convection heat transfer. This type of heat transfer situations is very common. They have got a lot of practical importance, particularly when we consider the case of, say, steam pipes, reactor vessels, furnaces. The heat losses which are happening from the walls of the furnaces, from heat pipes, okay, and steam pipes, from reactor vessels. So, all these things are happening just by natural convection, because you can consider that in case of a furnace, it is a vertical furnace. You have all the vertical walls, they are heated up. Inside temperature is very high, but outside there also will be some amount of temperature, though you have put some insulations that outside temperature may not be exactly equal to the ambient temperature. So, outside temperature will be higher, outside wall temperature will be higher than the ambient temperature, and because of that reason there will be some kind of again density difference, and there will be a flow about the vertical plates of the furnace. So, this flow is nothing but the natural convection, and the heat transfer to the ambient that is being happening due to this flow, due to the movement of the particles which is carrying the energy, thermal energy along with it, is called the natural convection heat transfer. Okay. Now, what we will see is that let us see some typical examples here. The very first case, In this case, let us see this. I am sorry. If you see here that there are typical free convection flow patterns of the fluids in the figure 1, and if you see that in the first case, here it is this is the cold plate, and we can see that these are cold parallel plates. So, this is a cold plate. So, what will happen, as because that it is a cold plate, it is not a hot plate. So, fluid coming in contact, fluid elements coming in contact with the plate will become colder, and as it becomes colder, they will try to move towards the downward directions, and it is going to the downward direction. So, other fluid element from the environment will try to take up this position, and these are of these fluid elements at these locations are of at higher temperature. So, this is the velocity distribution that has been taking place. The reason here over is the plate is placed, it is a vertical plate, it is placed in a stagnant medium condition. So, the medium surrounding it is the stagnant condition. So, the velocity, if you see the velocity at this point and at this point, these 2 points are becoming 0, and there will be a variation in the velocity, and this variation can be a nonlinear variations actually. Similarly, it is a case of like a just opposite to the furnace case, there are the parallel plates, okay, and then these are cold parallel plates. So, material will be cooled, it will come down, and then it will be heated up, and then it will go out. So, this is the same thing that is being happening like this, and this is the case where it is a hot plate, the upper surface is the hot. So, what is happening? A fluid particle is coming, it is getting heated up, it is trying to go up. So, this is the circulation that takes place. So, once the fluid particle is getting up, coming in touch with this, they are getting heated up and they are going upward. So, this position is remaining vacant. So, that is being taken care of by the surrounding fluid. So, they are coming like this and going upward. So, this is what is becoming the your flow pattern. Okay. Similarly, the case for in the case just opposite to this, here the cold the bottom face, lower surface is the cold surface. So, what will happen? Initially the fluid will once it comes to this contact, elements come in contact with this cold surface, they will become heavier, they will try to come down, and once it comes down, then some other fluid elements which are hot, they will try to take these positions. So, therefore, the circulation will be in the opposite to this the previous one. And if you see here, in this case, this is the cold surface, this is the cold surface, this is another way of having looking at these circulations. If this is cold surface, the material will try to getting cooled up, and that this is the surrounding fluids at a higher temperature, and the ones they are coming to the cold surface, they are getting cooled and they are trying to go towards the downward directions. Similarly, if the hot surface, the fluid element will come and they will try to go to the upper direction. So, this is the way that flow of the fluid element will take place. So, there will be a flow of the fluid, okay, and this is nothing but the natural convection or free convection, and this flow is being happening due to the application of temperatures. Okay. So, somewhere it is a hot place, somewhere it will be a cold surface, and surrounding. So, temperature difference between the surrounding fluid and the plate is of importance, and because of that reason there will be a net movement of the fluid particle that will take place, which is nothing but the flow or convection of the fluid elements. Similarly, if you see this is another figure. Here we can see that here it is a hot fluid, and we can see that there is again the boundary layer is just reverse of the cold fluid. In the cold fluid we have that in the boundary layer. So, we can say that this is the boundary layer and this is the stagnant region, this is the stagnant region, there is no flow. So, again this velocity profile will be like this, and we also can understand that the velocity profile here whatever is there, this can go even from initial stages it will be laminar, and then further if we go along the length of this, like we have seen in case of forced convection heat transfer, as we go along the length of the plate it becomes a turbulent flow. So, similarly, this is the case when you have a hot wire. So, from the hot wire both surfaces, all the sides of the surfaces are or if you say consider the hot wire in the vertically downward, this is the wire. So, it is that boundary layer will be flow. It will be like this, and the flow will be from like this way. And similarly, this is the hot cylinder. So, the cylinder, you can see that this is placed horizontally, okay, and so this is the front view of the cylinder. The cylinder is placed like this, and this is the front view of the cylinder, and so there will be the fluid elements which is coming in contact. They will be heated up and they will try to go upward. So, this is the plume that is being formed because of the plume of the hot fluid that will try to go upward. And once they are going like this, that they are making a boundary layer, okay, and the fluid element will move in the boundary region. In the boundary region only the fluid element will be moved, and beyond the boundary region, in this particular case, there is no velocity. Now, once if you have a velocity beyond the boundary range, then we can call it to be a combined free and forced convection. We will discuss later on, maybe in the next lecture we will discuss that. What happens is, when you have convection, forced convection of flow of the fluid due to some external force, in that case that becomes more and more dominant, that becomes quite dominant over the free convection situation, because the free convection situation, the flow of the fluid is not that high. So, therefore, what happens is the contribution to heat transfer won't be that much as compared to the forced convection heat transfer, where the flow of the fluid is very high and the contribution to the heat transfer will be very high. Okay. So, anyway, we should understand that what a natural convection is and try to find out that how this kind of situations should be tackled from two aspects. There are some theoretical aspects, like there is a boundary layer, and from the we can find out that how will be the heat transfer coefficient to be found out when there is a boundary layer flow like this. And the second case is, suppose we have some specific geometry, and then how to find out the empirical correlations for this kind of free convection situations for different kind of geometries. As we understand the empirical correlations, as we have seen in case of forced convection also, there can be several empirical correlations for free convection heat transfer, but the point here over here is that we have to see that it depends upon the geometry, it depends upon the orientation, it depends upon the shape and size of the plate. It depends upon that whether it is a cylinder, whether it is a sphere, or whether it is a flat plate. So, that geometry, it depends upon whether it is a vertically upward, whether it is inclined, or whether it is horizontal, the plate, okay, that is, or the cylinder. So, these things are also very important. At the same time, it depends upon that whether the surface of the plate is hot or the surface of the plate is cold. Depending on all the situations, the flow situation will change, and as the flow behavior changes, the heat transfer relationship also does got changes. And if you see, just for a glimpse, we will discuss little in details in the next lectures. If you see in this table, what we can understand that there are various geometries being said, like your vertical planes, then cylinder, horizontal cylinders, upper surface hot, lower surface cold, then lower surface hot, upper surface cold, then vertical cylinder where height is equal to diameter and characteristic length is equal to diameter, and then irregular. So, for different situations and different flow ranges, this will discuss that R A is nothing but the Rayleigh number. We will discuss in the later on. There are some constant values which can be picked up. So, this is a very important table which can be used up for some heat transfer calculations in case of convective heat transfer coefficients, that we will discuss in details in the subsequently in our lectures. Now let us first try to understand the free convection heat transfer on a vertical plate and some theoretical understanding to this. So, if I draw a vertical plate like that, so now our interest is that to understand free convection heat transfer on a vertical flat plate. So, this the solution of this kind of situation is relatively easier, therefore, we are taking up this just to have an idea and understanding on this. So, what happens is that the plate is hot and it is maintained at a temperature of Tw, okay, and So, this is the kind of behavior as we have seen in case of if you just give a 90-degree rotation, it is like a flow over a horizontal plate kind of things. And what happens is this region, we can say that this is the laminar region, this is the laminar region, and this is the turbulent region. Again, as we have seen in case of forced convection, there is laminar to turbulent transition that takes place after a certain height of the flat plate, and in both the cases there will be some temperature distribution as well as some velocity distribution. So, we will write that temperature in the surrounding fluid materials, it is say T infinity, which is the temperature of the, in this case it is not free stream temperature because there is no flow, but we will say that the surrounding temperature as T infinity, and typically say this is the say velocity profile already we have seen. So, we can say one thing that velocity at this point is 0 and velocity at this point is also 0. Okay. So, if I say, so this is the delta is the thickness of the boundary layer. As we move along, the boundary layer thickness increases. Now, what happens here is that this is the hot plate. So, fluid particle coming in contact, they are getting heated up and they will try to move upward. They will try to move upward. So, what is happening as we go along the plate, more and more molecules will add to this behavior, and therefore, there will be an improvement or increase in the depth of the boundary layer. So, more and more molecules will be coming into picture. Okay. Now, so what will to start with, we will again say consider a case of say we will take any particular region in the laminar flow region. Then what is happening actually if we consider a differential element, okay, and then consider the heat transfer problem there. So, for a control volume, and this control volume may be dx dy into 1. So, what is x and what is y? Let us try to understand. Say this is the x direction, this is the y direction, and z equal to unity. We will take that unit width of the plate. So, plate, this is the plate. So, this is unit width. Okay. So, that we will try to consider. So, then dx into dy into 1 will be the differential element in this boundary layer, and we know that if we apply Navier-Stokes equation can be developed from the differential element. We know that Navier-Stokes equation, we have used Navier-Stokes equation to find out the momentum integral equation. So, momentum equation, if we try to find out, we can find out the momentum equation using this Navier-Stokes equation or by cell balance approach. So, let us first write here that if we write say by if we can do the momentum equation, we can equation of motion, we can find out by Navier-Stokes equation or by writing a cell balance approach. So, what we will do, let us first write go by the Navier-Stokes equation. Okay. If I write, then what we have is rho, it is a vectorial form of Navier-Stokes equation is rho dV by dt is equal to minus grad P plus rho g plus mu grad square V. That is a very common form of Navier-Stokes equation, and if this is to be applied now, if I try to do this, because that flow is taking place along x direction. So, if we do x directional balance, x directional momentum if we consider, okay, then what we are going to get is we will write like this rho into del Vx by del t plus Vx into del Vx by del x plus Vy into del Vx by del y plus Vz into del Vx by del z. That is the total acceleration, and that should be equal to minus del p by del x minus rho g, because g is gx is against g. So, therefore, it will be minus rho g, and then plus mu into del square Vx by del x square plus del square Vy by del y square plus del square Vz by del z square. I am sorry, this will be del square V x, x direction momentum, and this will be del square V x by del z square. So, this is the Navier-Stokes equation along x direction, and so in the particular present situation, what we can say that, so we will assume that steady state. So, if it is steady state, then this part is 0, is because it is a steady state situation, and then we will say that no z directional velocity So, that means V d is equal to 0, okay. And then we have we will assume that del square V x by del x square is negligible, and del square V x by del z square is also 0. So, then what is happening? V x is not changing along with the z direction. So, then what is happening is V x is only changing along with y direction. Okay. Change of V x along z direction is not there. Change of V x along x direction could be there, but change of gradient of, that means dou x of del V x by del x, that is taken to be negligible. Okay. So, therefore, my final form or reduced form is rho into V x into del V x by del x plus V y into del V x by del y, okay. And this is equal to minus del p by del x minus rho g plus mu into del square V x by del y square. So, this is the relationship now happens. Now, what we will understand is that as it is a vertical plate, so the pressure gradient would be equal to the gravitational force. So, what we will write is that del p by del x pressure gradient, because of the elevation, is basically is becoming equal to minus rho infinity into g. Rho infinity is the density of the fluid when the temperature is at T infinity. So, rho infinity is equal to rho at T is equal to T infinity. Okay. So, therefore, then the equation is further, though we can rewriting the equation, we get rho into V x into del V x by del x plus V y into del V x by del y equals to g into rho infinity minus rho plus mu into grad square V x by del square V x by del y square. Okay. Now, what we will do? We will define a terminology that is called beta. It is nothing but volume expansion coefficient. This is called volume expansion coefficient, and then what happens is that beta is equal to 1 by V, V is the volume, into del V by del T at constant pressure, that we know, volume expansion coefficient at constant pressure, and this can be written as 1 by V infinity. V infinity is the volume at T is equal to T infinity, and then we have V del V is equal to V minus V infinity, change in volume because of the change in temperature in that differential location by change in temperature T minus T infinity. So, this is in terms of rho, if we write volume is inverse of the density, then we will get it as rho infinity minus rho by rho into T minus T infinity. So, then we can write the previous equation, we can write as rho into V x del V x by del x plus V y del V x by del y, okay, and this is becoming rho g beta into T minus T infinity. So, rho infinity minus rho is replaced by T minus T infinity, this, and plus mu into del square V x by del y square. So, this is called equation of motion. along x direction for free convection situation. And so, we have understood that for free convection situation that this is becoming the equation of motion. And one thing, now if we have to solve this equation, then we need to find out the expression for temperature. So, we need to solve, only we can solve these to get the velocity profile when we know about the temperature profile. So, we need to find out an expression for temperature also, or energy equation also. So, energy equation is as it is similar to forced convection case. It is V x into del T by del x plus V y into del T by del y is equal to alpha into del square T by del y square. So, this is the similarity relationship that we have seen in case of forced convection heat transfer, or in case of here, and also it is with the momentum equation. So, it is a similarity relationship is involved, where previously in this case we have mu by rho. If I take this rho to this side, it becomes nu into del square V by del y square. So, which is just changed by alpha, nu is replaced by alpha, which is called thermal diffusivity. So, only differential term is between these two momentum equation and the energy equation is the terminology which is related to pressure and gravity, which is nothing but related to the hydrodynamic condition. So, that will not appear in case of thermal or energy equations, okay? Thermal energy equations particularly. So, then if we have to solve this temperature profile and energy equations and as hydrodynamic equations, as we have seen that exact solution is a difficult one. So, like forced convection, we will try to go for that integral solution, that is the approximate solution to this. If we try to go for the approximate solution, then we have to use the momentum integral equation and energy integral equations. So, if we, and what is being done in that cases is that we will be assuming the velocity profile, we will be assuming the temperature profile, and try to apply or try to put them substitute these velocity expressions and the temperature expressions into the momentum and energy integral equations, and try to find out the expressions for heat transfer coefficient. So, our main target finally is to find out the expression for heat transfer coefficient. Okay. So, what is there is that if we try to see that momentum integral equation, if we try to find out, and that we know already we have seen for forced convection case without pressure gradient. We have seen that d dx of V infinity minus V x integral 0 to delta rho V x into dy has been equal to tau w. Now, in the present situation, here for free convection, we know that V infinity equal to 0, because the surrounding fluid is considered to be at stationary condition. Okay. Now, what happens is surrounding fluid is at stationary condition, then our this equation becomes d dx of 0 to delta rho V x square into dy, and that is equal to minus of tau w. Now, what happens is in case of free convection, we will add up the buoyancy force, adding the buoyancy force in the equation, what we get is d dx of 0 to delta rho Vx square dy equals to minus tau w plus, we know that this is 0 to delta rho g beta t minus t infinity. Already we have seen that rho g beta t minus t infinity, and this is into dy, that gives the buoyancy force. So, then we can write this as d dx of, if rho is constant, Vx square into dy is equal to minus tau w by rho plus nu, tau w is equal to mu into this. So, we can write the nu into minus mu into del Vx by del y at y equal to 0, because tau w we know it is mu into del Vx by del y at y equal to 0, and yes, and plus we will have 0 to delta rho cancels g beta t minus t infinity into dy. So, this is happening to be the situations. Now, what we need is, we need two things. We need a temperature profile, we need a velocity profile to be assumed. Okay. Now, for the standard analysis of the boundary layer over a flat plate, the temperature profile has been assumed to be like this: T equals to A plus Bt plus Ct square. So, it is a second order polynomial. Now, what we will write is, a second order polynomial with respect to y. So, A plus By plus Cy square. And now, the boundary conditions are, we can understand, at y equal to 0, T equals to Tw, that is the wall temperature, y equals to delta, again T equal to T infinity, okay, and that is the surrounding fluid temperature, and at y is equal to delta, del T by del y would be equal to 0. That we also can understand. Once we reach to the boundary layer, then that temperature differences won't exist. Okay, they will be negligible. Okay. Therefore, based on that, we have already seen this. We are not going to do this just calculation. So, if we put all this over here, then our temperature profile happens to be like this: T minus T infinity by Tw minus T infinity will come as 1 minus y by delta whole square. So, this is a kind of velocity profile that we are temperature profile that we are going to get. Now, if we take again with the standard practice, if we take a velocity profile of this kind, like Vx equals to say a1 plus b1y plus c1y square plus d1y cube. We have seen this kind of analysis in previously also. So, here the conditions are at y equals to 0, our Vx is equal to 0. At y equals to delta, here that is the important thing, that Vx is again 0. Previously, in case of forced convection analysis, we have seen that at y equal to delta, Vx had been V infinity, but here the V infinity is equal to 0. That is no movement of the, no velocity of the surrounding fluid. Surrounding means surrounding the boundary layer. Okay. Now, again at y equal to delta, we know that del Vx by del y is equal to 0, and at y is equal to 0, okay, we will write del square Vx by del y square will be equal to minus g beta into T minus T infinity by nu. How do we get this expression? We can pretty easily understand. Already it is coming from the equation of motion. So, equation of motion says, already we have discussed that according to the equation of motion, rho into Vx into del Vx by del y, sorry, del Vx by del x plus Vy into del Vx by del y, which we have just seen, okay, from the Navier-Stokes equation, and this is equal to rho g beta into t minus t infinity plus mu into del square Vx by del y square. So, now at y equals to 0, we know that Vx equal to 0, we know that Vy is equal to 0. These are called no slip conditions. Okay. So, when we go for these no slip conditions, then what we get is that mu into del square Vx by del y square equals to rho g beta into minus into t minus t infinity. Okay. Then del square Vx by del y square is equal to minus g beta t minus t infinity by nu. It will be by mu, mu by rho is equal to again nu. So, I will write properly. So, it is becoming like this. So, this is the conditions, that is what is the condition that is being used, which is obtained from the equation of motion for x direction. And then once we got that, then we have to get the expressions for Vx, and Vx is equal to, or Vx by u is equal to y by delta 1 minus y by delta whole square, where u equals to beta delta square g t w minus t infinity by 4 into nu. Now, what is this u? U also can be considered a kind of velocity term. Okay? As you try to see that unit of u, if we try to see what is the unit of u, it is beta into t. Beta is the coefficient, and into t, beta into t is the unit length. So, beta is per unit Kelvin. So, beta if I write 1 by Kelvin, and then delta is the thickness, boundary layer thickness. So, into say meter square, okay. Then g meter per second square, into this temperature is Kelvin again, and you have into 1 by this nu is nothing but diffusivity, it is a momentum diffusivity, and diffusivity unit we know it is meter square per second. So, this happens to be like this, then this cancels, meter square cancels. So, this is becoming meter per second, which is having an unit of a velocity. So, u is a kind of velocity that we can consider, and which is a fixed quantity with respect to T w and T infinity and delta. So, for a particular if we consider the boundary layer thickness, okay, delta, and once we reach to the boundary layer thickness, then we will be reaching to T infinity, and then we will be getting a expression for u. Okay. Now, once we know that, then what we can write, if we put the velocity profiles into this, we will get in the momentum, putting the velocity profile, okay, in the momentum integral equation, what we get, that d dx of 0 to delta u square y by delta whole square 1 minus y by delta whole square equals to minus tau w by rho plus 0 to delta g beta into t minus t infinity into del y. Now, what we have to do, t also is a function of y and delta. So, however, before we put that, we can just, if we do the working out with the left hand side of this, will get, or 1 by 105 d dx of u square delta, this is equal to 1 by 3 g into beta into T w minus T infinity into delta, okay, and minus tau w by rho is nothing but nu into u by delta. So, this is say equation 1, and so by putting the expression of, here also we have to put the expression of T w, T minus T w we know, T w minus T infinity into, as we have seen that we have to put that expression T minus T w is equal to T w minus infinity into 1 minus delta y by delta whole square. So, if we put this expression only and then do the integrations, then we are going to come up with this equation. Now, similarly, for energy integral equation, if we try to see that for energy integral equation, it is like this, that d dx of 0 to delta is similar to what we have seen in case of forced convection, T minus T infinity into dy, and that is happening to be minus alpha into del T dt by dy at y equal to 0. And we know already that T minus T infinity by T w minus T infinity equals to 1 minus y by delta whole square. Now, once we have that, then we can, if we put this expression for velocity, substituting the values of expressions for Vx and T minus T infinity, and then integrating subsequently, we get, what we get is 1 by 30 T w minus T infinity into d dx of u into delta is equal to 2 alpha into T w minus T infinity by delta. So, this is say equation number 2. Now, the question is that solving the equation 1 and 2, there is a typical further assumption, and if we see from the velocity expressions and from reasoning from velocity expressions and with reasoning, we can say that u is proportional to delta square. We can see this. We can say that in the velocity expression is like this, u is proportional to delta square, that is what we have seen. And similarly, once we get u is proportional to delta square, similarly we can then we can say that from equation 1, delta is proportional to x to the power 1 by 4. Okay. Then what we will write is, we will write as C1, u is equal to C1 x to the power half, and delta is equal to C2 x to the power 1 by 4. So, we will consider this, where C1 and C2 are constants. Okay. Now, once we know the value expressions for once we understood this, then what will be done is, if we incorporate the new expressions of u and delta in terms of in equations 1 and 2, we get what we get? We get 5 by 420 C1 square C2 x to the power 1 by 4 equals to z beta TW minus T infinity into C2 by 3 into x to the power 1 by 4 minus C1 by C2 nu x to the power 1 by 4 and 1 by 40 C1 C2 x to the power minus 1 by 4 equals to 2 alpha by C2 x to the power minus 1 by 4. Now, after solving the above two equations, we get C1 is equal to 5.17 nu into 20 by 21 plus nu by alpha whole to the power minus half. Now, you have g beta TW minus T infinity by nu square whole to the power half, and we have C2 equals to 3.93 okay, 20 by 21 plus nu by alpha whole to the power 1 by 4 into g beta into TW minus T infinity by nu square whole to the power minus 1 by 4 into nu by alpha whole to the power minus half. So, these are the two expressions we get for C1 and C2, and then we get delta by x. So, the boundary layer thickness delta by x is equal to 3.93 Prandtl to the power minus half into 0.952 plus Prandtl to the power 1 by 4 Grashof x to the power minus 1 by 4. Okay? And we know that already we have seen that Prandtl is equal to nu by alpha, and also we have seen in some lecture in lecture 3 in module 4, while we have discussed the dimensional analysis for free convection heat transfer, that we have found out an expression for Grashof number, a dimensionless group that we have found out as a Grashof number. So, we are saying that GRX, which is called as local Grashof number, that is equal to GRX, and this is G beta TW minus T infinity by nu square into x to the power cube. So, this is already we know. Now, we can find out the Nusselt number from the relationship that wall heat flux QW is equal to, or wall heat transfer wall heat flux QW dot W is equal to minus K into del T by del Y at Y equals to 0, and that should be equal to the heat transfer coefficient, the local heat transfer coefficient Hx into TW minus T infinity, that is the by convection. Okay. From there, we can find out that Hx is equal to, by putting the value of delta T by Y at Y equal to 0 from the temperature expressions, we can find out this is equal to 2K by delta. So, or Hx x by k is nothing but local Nusselt number, and that is equal to 2x by delta. So, we can find out that Nusselt number, local Nusselt number is given as 0.508 Prandtl to the power half into 0.952 plus Prandtl whole to the power minus 1 by 4 into Grashof x to the power 1 by 4. And then this Grashof number is called, it is like a Reynolds number in case of a laminar flow situation, Reynolds number in case of forced convection, that already we have seen, and this Grashof number dictates the flow conditions depending upon the values of the Grashof number. When Grashof number, Grashof say x is between, or rather greater than 10 to the power 8, we call it to be turbulent zone. and this is for air over vertical plate. So, this critical Grashof number is found to be within 10 to the power 8 to 10 to the power 9 for various fluids, and this value to decide whether the flow is turbulent or the flow is laminar. When it is 10 to the power 8 to 10 to the power 9 greater than that, then we say it to be in the turbulent region. Otherwise, if it is lower than that, then we tell it to be in laminar flow region. Okay. And then we have already done it, that h bar is equal to 1 by L integral 0 to L h x dx. This is the average heat transfer coefficient, and this happens to be, in this case, it is something different, 4 by 3 h x is equal to L, and then by this way we can find out the average Nusselt number also. Okay. Now, so this is the way we can find out average Nusselt number. We can find out again Nusselt average with based on L will be equal to h bar based on L, x is equal to L into L by k, that is. So, we have to put the expressions for h bar x is equal to L, and we will get the expression for the average Nusselt number. So, this is the way we can find out the Nusselt number, we can find out the heat transfer coefficient, and then once we know the heat transfer coefficient, then now it is h into A into delta T is the total amount of heat transferred. Okay. So, this is about the theoretical development in a boundary layer over a flat plate to find out the heat transfer coefficient values. Now, if I try to just discuss one problem, a very conceptual problem. So, suppose we have a bucket and there is a liquid water. So, particularly during winter, what people does, they put some immersion heater here, and say this immersion heater has got some coil, and there is a connection over here, and there is a plug connection. So, there is a immersion heater over here. People put this immersion heater to get the liquid heated up in a bucket. Now, what happens? What is the functionality for here, that once we put the immersion heater here, and if we just put the switches on, then this coil will be heated up, and once this coil is heated up, this heat will be transferred to this liquid water, and this water will be heated up. Now, if you have noticed that what will be the heat transfer mechanism in this particular situation, that is the question. Question is, what is the heat transfer mechanism? Now, here one thing is pretty clear, that there is no flow of the fluid. So, convective heat transfer is not there. Heat transfer. Then what is there? If you see, till this layer, it is heated up, and once the fluid heats up, it will go up, and the other fluid will come down. So, this circulation. So, up till the bottommost part of the coil, till the top of the bucket, top layer of the water in the bucket, in this region there will be free convection or natural convection. Because it will be heated up and it will go upward. But as we go down in this part, in this region, here it will be by conduction. Because the fluid once heated up, they will try to go upward, this fluid will never come to this. So, from this fluid to this fluid, the heat will be transferred by the mode of conduction. So, there is a combined mode of heat transport here. Part of the fluid is being heated up by the method of natural convection, and lower part, bottommost part of the fluid is getting heated up by the method of conduction. And therefore, if some of you have noticed that if you just put up the switch and take out that heater gently, then we will find initial certain depth, till the depth of this immersion heater, we will find that it is heated up, but after a certain depth, we will find that this liquid is, this water is cold. So, what we have to do? We have to do some kind of stirring to have an uniform heating finally. Okay. So, this is what for today. We will stop here. From next class, we will discuss on the some important empirical correlations that is available for heat transfer, natural convection or free convection heat transfer, and we will try to take up a few problems to see the applications point of view. Okay. Thank you very much.